Thank you very much. Yes, so my name is Olaf Stramer. I will start the presentation. I share it with my colleague Michael Weidner. And at first, I want to introduce us a little bit. My name is Olaf Stramer. I'm responsible for the industrial quality testing team here at Siemens, and we are providing a solution that is called Enovis. It is used on several places in the industry, in the production line. And today we will present you a short overview about the portfolio. Then I will tell you something about the Enovis end-of-line test. Afterwards, Michael Weidner, he is Business Development Manager in our team, will explain you the Enovis NDT solution. Yes, and then I hope we will have some time for a discussion for answering your questions that you may put into the chat so that you get an impression what we are doing. Yes, before I go into detail, a short introduction of our team. You may think, yes, IQT, I never heard about this at Siemens. That's true. We are part of Siemens since 2019, but we are not a new team at all. We were founded in the middle of the 90s in a small mid-sized company called MEDAF Digitale Signalverarbeitung. It's a German company. It is located near Erlangen. And in this company, we formed our team for noise and vibration tests in the industry in the middle of the 90s. In 2012, MEDAF was bought by Saab, and some years later, we changed the company name. And in 2019, our team, our noise and vibration test team, switched over to Siemens Industry Software. That's why we are here, and we are glad that we can use the workshop at ARCAM to present our solutions a little bit. So the overall portfolio, we have three main applications that we address in the industry. The first one is the end-of-line testing. Here we are talking about every items, or we are talking about a production line where a certain item is produced, and the item at the end has to be tested. Items could be electric motors, pumps, also complete aggregates like washing machines, dishwashers, refrigerators, coffee machines, everything that you have in mind that makes noise or vibration during operation. This can be tested by the end-of-line testing system. The goal of this system is to detect faults and to identify them. That means the first goal, of course, is to be sure that only items which are error-free or fault-free will be shipped to the customer. But we not only want to tell you this item does not fulfill the quality criterions, we also want to explain you why. That could help you to improve the production quality and to avoid such faults in future. Then the next part of the portfolio, the next application is non-destructive testing. This is something that Michael will explain you more in detail. Here we use the technique of resonance testing to test parts, not assemblies like a motor, but a part like a belt pulley, as you see it there on the picture. And the technique that we use there is quite old. It is used in pottery since many thousand years. You take, for example, a cup or a pot, you hit the pot, listen to the sound, and if the sound is okay, then you know there's no crack inside, the part is okay. That's what we are doing here in a more industrial scale, and Michael will explain it more in detail, as I mentioned. Yes, the third application is process monitoring. Also, process makes noise and vibration. And if we have automated processes, then the noise and vibration should always be the same. The process has a certain kind of fingerprint. And if something went wrong in the process, there's a high probability that also this noise and vibration fingerprint changes. And our Simcenter Enovis monitoring system is able to detect these changes and to set an alarm. For example, what you see here in the picture is the production of joints. There's a ball joint where the ball is pressed into a pen, and during that process the pen can break, and this characteristic noise can be detected and alarmed by the monitoring system. Yes, now you see a lot of machines there on the pictures, so it would make sense to explain you a little bit what is our scope of delivery. So one slide about the system overview. We deliver everything that is needed to do the noise and vibration assessment. That starts at the right sensor, a sensor that can be used in an industrial environment. Then, of course, we have a hardware that records the sensor signals in a high quality, and on the other hand is also industrial proof. And then, of course, the software is needed to do the feature extraction, the calculation of metrics to perform the identification of a fault. Yes, and then we help you to put this all in the production line by technical consulting, preliminary studies, commissioning, training, and of course we also do after sales support. That means we know that many of our customers are no NVH specialists, and so we provide all the after sales support that also a non-NVH specialist can deal with this system to provide a high production quality. Yes, that's what we are doing here. We help you to fulfill general objectives. The first one is the quality, of course. That means if you have a production line, if you produce parts or assemblies, of course, it's quite important that defective parts are sorted out and that we also are able to rate the vibration and noise quality. Those are two different things. In the end of line test, we not only try to filter out parts that are loud or that vibrate too much, we also use noise and vibration as an indirect measure to detect faults that may lead to a breakdown of the item in operation. For example, if there is a bearing damage on the pump of or on the grinder of a coffee machine, then it's quite likely that the coffee machine will break after some hours. And we are also able to detect such defects by looking at noise and vibration and prevent you from delivering products that will fail during the warranty period. Then on the other hand, another important objectives is the so-called zero fault production. Especially for complex things, maybe you are a supplier for the automotive industry. There we have very complex parts at the end. And we need to provide a high quality for every small part. It's a question of probability. If you have a complex assembly that is assembled from, let's say, 100 sub-assemblies, and the quality of these of each sub-assembly is in the range of 1% is faulty, then from statistical point of view, there's a high probability that none of the complex complete assemblies will be free of fault. And that's why minimizing the faults and actually provide a zero fault production is important. And we provide measures for that to identify faults that never occurred before. Yes, and at the end, if we provide high quality standards, if the system is able to identify a fault and help you to avoid it, this will lead to an added value. Or another, yes, and we are doing this for many customers in the world. We have a lot of customers in Europe. We have customers in Asia and South America, North America. Yes, the slide is a little bit older. There are more than 1,000 systems mentioned here in the field. I think we are about 1,200 systems in the field running currently 24 hours, 7 days to provide high quality for our customers. Yes, that's short introduction. Now I will introduce the end-of-line test. At first, also task benefits and typical example. Then we go through the measurement chain, highlight a little bit the sensors, the data acquisition software, interfaces to the production process, and I will explain you a little bit how to set up such a system. Yes, end-of-line objectives. It's only another representation of the slide I showed you before, but it shows also that the end-of-line test based on noise and vibration is not only an additional effort, which it looks like if you look at the customer requirements. The customer want to be for wants part that are compliant to the quality standards, want an objective testing, want defined criteria. That's at the first hand an additional effort. But if you do it in the right way, then the test will provide you extra information that you can use to reduce rework, to improve your production quality, to avoid faults in the production line, to improve the production line there where it's necessary. So for example, if you provide a top 10 lists of fault, then you can concentrate on the 3 fault that happens most often and avoid them. So you can very effectively increase the production quality based on the results that the end-of-line test system delivers. So at the end, we provide an added value. So the example, what happens, sorry, it's from automotive industry, but we do a lot things there, and it's also very impressive what we can do there. What you see there is a piston of an internal combustion engine. And there's a mark printed on the top of this piston, which shows you in what direction the piston has to be mounted. But what happens if this mark is printed in the wrong way on the piston? Then all the pistons will be built in the wrong position or in the wrong direction into the engine. It is possible to do this. There's nothing blocking. You can build it in. You can complete the whole engine, put it on the test bench. Everything is fine. But then at the end, you would deliver a lot of faulty aggregates, especially if this not only takes place once, especially then if the whole machine is programmed in the wrong way and you have some hundreds of these pistons on the line. Then you can imagine every engine would lead to costs of, let's say, 1,000, 2,000, 3,000 euros. If you have 100 or 200 of these items in the line that will be delivered to the customers, then it's a quite big financial loss that could happen. So this is something that we have to avoid. And this is possible based on noise and vibration, for example. You see here in the piston these valve pockets where the valves will fit in if the piston goes up in the cylinder. And if they are not in the right position, then the pistons slightly, the valves slightly touch the piston. It has no influence on the torque or on other metrics. You only hear it in the vibration. And you can set a metric to identify this fault and to prevent delivering faulty items and to prevent high costs to the production line. Yes, this is what we are doing there. I also have a video that shows you a little bit how it looks like in the production. This is a production of transmissions. Here the system is integrated in the complete test bench. Now the item is prepared for testing, and after a certain time it is feeded into the test bench. And now the whole test runs automatically. So the item is put it in, is adapted. The inputs and the output shafts are adapted. Also the sensors will be adapted. You see here our industrial vibration sensor. It will be pushed against the measurement point, and then also a microphone is put it into position, and afterwards the test run is performed automatically. Here you see the microphone, and then at the length of this video, which is about 1-2 minutes, the complete test is performed. And during the tests, the ANOVA system shows the results and transmits a list of metrics to the PLC so that the PLC can decide what to do with the item. If noise and vibration test is okay and all the other tests are okay, the item will be shipped. Otherwise, the item will be sent to a repair station, and based on the identification of faults that we have done, the item will be repaired. So this is a typical example. Sorry for being automotive, showing you an automotive sample again, but we can do this, of course, also. We do this also for other applications. Yes, now let's talk a little bit about the measurement chain. You already have seen our sensor there. Especially if we want to do automated tests, then it is quite important to provide a sensor that is able to run in an automated way. This is not possible with the standard sensors as you see it here, since they have to be connected or glued or screwed on the test item, or you need a magnet to put it on the test item. And this is something that is not so easy to automate. And on the other hand, if you do not have a good contact from the sensor to the device under test, then the resonance frequency and therefore also the bandwidth of the signal that we can use for fault identification dramatically goes down, so that we will not be able to identify faults that lead to signals with a frequency of, let's say, higher than 1 kilohertz. And this is quite very low. But if you use the right sensor, like this tip, like this KSO3 tip, then the resonance frequency is high. You see it here in these pictures. The resonance frequency of this sensor is above 10 kilohertz, so that we can use a frequency range up to 8, 9 kilohertz to assess the vibration emitted by the device under test. Besides these sensors, we also use microphones. We use them for frequency range up to 75 kilohertz. It's much more than the human being can hear. And we also can use laser vibrometers up to a frequency of 100 kilohertz. Laser vibrometer, especially the industrial vibration sensor IVS 500, is very suitable for industrial applications. We use them and also the older types like the EVS 300 since many, many years, since more than 20 years, and we have a lot of good experiences in the production line with these sensors. There are some things that we have to take into account, but our software and also our hardware configuration is able to deal with it. Yes, and then of course, if we are measuring at the production line, then we have to take care that we measure in an objective and repeatable and reliable way, especially if you have several production sites all over the world. You want to have the same quality of measurement of test in all of your plants, and therefore sensor calibration is quite important. Of course, we provide the calibration tools for our sensors and also standard calibration tools for the microphones, so that you can calibrate your measurement chain or your novice measurement chain. And the calibration is also supported by the software, so that it is so easy that it can be done by a standard maintenance operator, and the time needed for calibration is about 5 minutes per sensor. And so you can do it by yourself, and you can also use the calibration to check if the system runs under good conditions. Yes, if we place the vibration sensor, then in many cases we also need some supplementary information for rotating machinery. This is the so-called tacho signal. To extract signal, noise or vibration components coming from rotating machinery, so-called angle equidistant signal processing is used. Methods, as you may know, as order analysis, for example, or angle synchronous resampling or something like that. To do this, ANOVIS does this as one of the major or the main signal processing methods. To do this, a tacho signal is needed. And to do this in a high precision at high speeds, for example, if you want to test a vacuum cleaner turbine, which runs at 10,000, 12,000 RPM, then it's important that we provide a precise tacho acquisition. Our tacho acquisition uses a sample rate of 48 megahertz, so that we have a very high accuracy, which allows us to measure under high speeds and high speed gradients. Also ramping up from 0 to 250,000 RPM, as we have it in an exhaust turbocharger test bench. This is something that we are used to with our system. Yes, and then we are at the hardware. The hardware is called Simcenter Novice Signal Recording Device. It's a modular hardware. We have it available in different housings. As you see it here, a big 19-inch box where you can put up to 8 modules in, or a small DIN rail housing that can be mounted on the DIN rail in the cabinet, which provides up to 4 signal channels plus 4 Tahoe channels. Both units are connected to the PC via Ethernet. That means we do not have special interface cards in the PC. We do not need special slots in the PC, or even we do not need a special PC. Usually, uh, we are very glad if we could use your standard PC that you use all over the plant. It makes life easier for us and also easier for your IT. So therefore, we do not need extra hardware requirements. The signal recording device is connected via Ethernet, and that's it. Then the basic modules have 2 noise and vibration signal channels per module. They have a 57 kilohertz bandwidth, have an up-to-date 24 bits analog digital converter, have integrated filters, high quality analog input signal processing, and we also can connect ICP or IEPE sensors directly. And the inputs are also supervised. It's sometimes quite hard to, but our system has to deliver or has to have a higher quality than the production line has. Otherwise, we would not be able to solve the measurement task or the test task. This is something about measurement system analysis. To provide this, we also do a lot of self-supervision of the system. And one part of it is that we supervise the sensor, supervise the ICP power supply, so that we are able to alarm a sensor defect if the cable is broken, if the sensor is not connected, or if something else went wrong. Then, as already mentioned, we have trigger tacho inputs, also 2 per basic module. And then we have optional modules for switching between several sensors, for connecting low changing measures like temperature, torque, current to the system, so that we can provide an overall signal recording. Yes, when the signal is recorded, it will be fed into the PC, into our software. And also this software is modular. That means we can switch together a certain signal processing, a certain test regime that is necessary to do a certain test by mouse click. Therefore, we have modules that we call flowlets. We can instantiate them based on a library where we have a lot of signal processing functionality included, and we can connect them by mouse click so that we have a new application within some hours available for a new test. So therefore, in general, we do not need to program. If you have a completely new application for us that we never have seen before, then in 99% of our cases, we do not need to write any line of code. We take our system as it is installed, as it is tested, as it is available reliably, and configure the setup according to your needs. And it's the same for the interface. The view that you see here is also can also be configured by mouse click so that it fits to your application. For example, that's what you see here on the screen is something that may be interesting for the expert to see a waterfall, to see some lines, and at the end of line test, you may only be interested in this table with the green lights to tell you that every item is okay. And so we can configure it in that way that all the other things are hidden and you only see the list of features. Then our system provides online and offline mode. From every test, we can record all the raw data, all the measurement curves, so that you can analyze them and use the data to optimize the signal processing offline conveniently on your office PC. Yes, here's a short overview about the modules that we provide with our system. We start from signal conditioning, calibration, differentiation, integration, RPM channels, tacho pulse conditioning, go via triggers to the analysis function, frequency order analysis, angle synchronous resampling, capstrom, synchronous capstrom, third octave analysis. All these things are included by standard into our system, as well as the metrics like frequency and order spectra, order level tracks, harmonic levels, level tracks, and whatever. And also we have also some high sophisticated modules like psychoacoustics to provide psychoacoustic metrics, and also classifiers that adapt automatically to the production, like our chameleon. So that means all this can be used by mouse click so that it's quite fast to provide a solution. Yes. Now I try to explain you a little bit how we set up the system, what are the steps to build up a new application. We start with the bandwidth requirements to understand what sensors do we need, to understand what are the signals that we have to extract from the overall signal that we have to assess. Let's take an electric drive, for example. Here we have the shaft and the bearing orders that can be used to analyze unbalance, alignment errors, bearing damages. Then we may have gear orders and sidebands of them. They give you information about the tooth length and about the quality of the tooth themselves. So we are able to detect tooth damages there, tooth length, shape issues, and other things that may have went wrong by machining the gears. Then we have the motor orders and the sideband lines. We can use them to detect eccentricity of the rotor of an electric motor. And we can also use them to find deviations of the magnetic field. For example, if the wrong magnets have been built in. And we see, of course, also the inverter frequencies and component vibrations that also can be used to find out if there are loose parts on the item or if we have any kind of resonances. Yeah, so now in the next slide, I want to show you how we extract these items from the overall signal. What you see here is the signal that we acquire with our sensor. And now we want to assess only a part of this signal to find out if a certain fault is happens in the device under test. And therefore, we use the so-called drill down. That means we start with a basic analysis that helps us to extract the signals that we are interested in. For rotating machinery, this could be, for example, order analysis. For the inverter frequencies, this is inverter frequency demodulation. And based on this, we extract all the signals, for example, for order analysis, all the signals that are synchronous to the speed of the test item. Then in the next step, we calculate a measurement curve. This could be an order spectrum to assess harmonic signal components. And this helps us to separate all angle synchronous signal components from each other. And now from the position in the order spectrum, we know, for example, the origin of these orders, for example, for gear mesh orders, for pole frequencies and all these things, we know in advance at what position we have to look at in the order spectrum. And so we can assess some special levels, and then we will have a metric. For example, what you see here are pole frequencies of an electric motor, and we take them, calculate an harmonic level, which is our metric to assess the quality of the electric motor. And the metric is a single value. Every point of this curve is one measurement. The blue ones are production line items without faults. The purple ones have another fault, but not a fault in these pole frequency. And the red ones have an issue in the motor. And then based on this, we can set a limit so that we can be sure that the good items are within these limits and the bad items are outside. We set the limits, or we also assess these limits. We do this based on measurement system analysis, calculate the CPK value to find out if this metric is able to test the process. So if the CPK value is bigger than 2 or 3, then we know, yes, we are safe. This item will work. Yes, that's the way how we set this up. Therefore, we use several kinds of analysis function, not only the order spectrum, but also, for example, an order capstrom to find damages. Or even if we have an order spectrum, or any kind of curve, we can use quite complex metrics to do a distinction between good and bad, even if it's not really visible on the first view. Here in the order spectrum, the blue lines are production, the red lines are faulty items. You see there's no place here in the spectrum where we know line where we have a gap between good and bad. But if we take the relation between the gear mesh frequency and the sideband lines into account, we can derive a metric that allows us to have a gap, to set a limit. Yes, that's how we do this for faults that we may know. But in one of the first slides, I mentioned the word zero fault production. And the question is, how can we handle this based on these metrics? Not really. And therefore, we have another method to do this. This is called the chameleon process. It's in kind of continuous process. We have our chameleon is providing statistical limits. That means based on all the parts that are produced in the production line, we define a statistical limit for the complete measurement for curve, for the complete order spectrum, for example. And if the part is inside, everything is okay. If one item has a measurement curve that is outside of these statistical limits, we call this detection of a suspect item. Then, since this is only a simple limit curve, it's quite easy to do an analysis of the root cause to understand why chameleon thinks that this part sounds suspect. And based on this information, we can do a diagnosis. That means we can find out, is it really true that we have this kind of fault? And if yes, if we identify the fault, we define a new metric, we implement or we set up a new metric in the ANOVA system so that at the end we have a new identification metric that from now on we will identify this kind of fault. Yes, this is how it looks in practice. Here you see the typical interface of the ANOVA system. Two metrics have been defined up to now. Motor unbalance issue with the gear mesh stage number 1. Now we have the picture like this. All the two metrics are green, but chameleon says, this sounds suspect. In the second step, we could do an analysis based on these on the chameleon output, and here we find out, yes, order 5, order 10, order 15 are outside of the typical production range. This may be an issue with the electric motor. Yes, and at the end, we can set up a new metric to identify this fault also in future. Yes, this is the step how we identify new faults in the end-of-line test system. Of course, integration of the system into the production line is mandatory. We provide several interfaces to connect to your automation system so that the system can be integrated in the production line very easily. And we provide, as I already mentioned, also offline analysis functionality so that you can use ANOVAs by solving your quality testing tasks. So that's from my side. Now I hand over to Michael to the ANOVAs NDT. Thank you very much.
Thank you, Olaf, and welcome to the second section of our presentation. I will introduce the non-destructive testing of single components with Simcenter ANOVAs NDT. As you already know, the core function of Simcenter ANOVAs systems is the measurement and evaluation of noise and vibration signals. Therefore, it will not be too surprising that our NDT method is acoustic resonance testing, or short ART. Within the next few minutes, I will explain its principle. You will see which kinds of defects can be detected, and you will get an impression of how it looks like in practice. So let's start with the principle. Acoustic resonance testing evaluates the state of a component based on its natural frequencies. These frequencies are physical properties of a component, which are determined only by internal characteristics, physical properties. I will enumerate them later. And conspicuous parts that behave significantly other than the rest, get sorted out. So, when do you test with ANOVAs NDT? End-of-line testing is the normal case. I know two reasons for the rare case of inline testing. It's if it's an expensive production step which follows. So all bad parts should be sorted out before. Or B, if a subsequent production step makes it difficult to measure the natural frequencies of the part. This could be an impregnation with oil or resin. Then how do you test and what can be detected? ART is a fast method. So there is no reason for testing less than 100% of all produced components. And ART offers assessment of the full component volume. And what shows up in the vibration signals? Well, all changes in geometry, changes in mass or density, changes in microstructure, elastic modulus, stiffness. These are the physical properties which are directly related to the resonance frequencies. From our experience, the damage which shall be detected with a novice in most of the cases are cracks. And what do you test with a novice NDT? Well, why do you test with a novice NDT? Well, often the customer requires a 100% test because the parts are either safety critical, for example, in brake or steering assemblies, or they are function critical. So this is the case when a failure can severely damage expensive assemblies like a gearbox. And this brings me to the message of this graph. Okay, there is a customer requirement, which means additional effort. A novice can now identify defective components, task solved. But why do many of our customers apply a novice NDT even if the end customer does not require it as a mandatory test? Well, they avoid customer complaints. They use a novice NDT to learn about their production and improve their production. And they use the 100% testing for marketing and as an advantage in competition. For example, when they apply for the production of a certain part. So this is the additional value you can get from it. You might think, well, we have serious production, but we do not have such a high production volume of one single part type. In this case, please consider you could test several part types with only one novice NDT system. This has become more and more common throughout the last years. So what you need is a setup for each part type consisting of a solution for the mechanical transport and a part support that fits to its geometry and it enables reproducible sound excitation. And finally, an novice test setup parameterized for the respective part type. Okay, but now no more slides. Follow me to our lab. Oh, we do not have an automated system production line with a testing station in the basement. But what I can show you is how a novice NDT looks like and how it works. So I start the video.
Michael, we cannot hear the voice. Maybe you should stop sharing, and if you share again, check the button include computer audio.
Okay, thank you. So I go to this panel. And now Include computer sound. Okay, so now it should work.
No, sorry,
Again?
we can't hear you.
Oh, okay.
Maybe you explain a little bit what you are doing.
Well, we could run it and I can talk to it. It's like
Yes.
synchronizing. So what I show you is acoustic resonance testing with a Novus NDT. It consists of hardware for excitation. What you see is a slide. It provides multiple degrees of freedom, like height, angle, and everything. And it's used for small and lightweight parts. And sensor is a broadband microphone. And from there, it goes to the Novus signal recording device. It controls the part excitation. It controls the signal recording. And well, it's connected via Ethernet, as we know, to the industrial PC. And there the metrics and the assessment results get calculated and evaluated. What you see is a switch cam. For this part type already, there is a test setup defined. It contains all the settings you need to test it. For example, for the microphone, we need the calibration data, the trigger parameters for extracting the right piece of the recording, the detection windows for extracting numbers for the resonance frequencies, and well, of course, the software which shows the results. And as Olaf already mentioned, the user interface can be configured according to your needs. So there also can be different modes, like an operator mode and expert mode. The whole thing starts with an adaptation to what is currently the typical behavior. You need at least 20 parts for it. And what I do right now is to record normal with which we can compare the behavior, the sound behavior of the next part under test. So I use a foot trigger to release this pin at the slide. And in the background, you see the spectrum for each part. And under the green bar, there is the word adaptation. And, well, you see this is nothing you want to perform manually. So I do this with, let's say, 50 or 100 parts in the laboratory. But the system is for automation. It's for automated operation in a production line. So I guess we are through. This was the first part which was assessed. It was an okay part, another okay part. Well, it wouldn't be fun if we did not have a cracked one. This is that one, but this is not a good ending point. It's smooth. This looks much nicer. Well, this was the principle of testing with a slide for the small and lightweight parts. The more common kind is the part excitation with an impact device. You hit the part with a little electromechanical hammer. Here it's the belt pulley for electric power steering. It is positioned in a part settlement. There is some green rubber material for vibrational isolation between part and its support. It's placed there reproducibly so that we get a constant signal from it, no matter how often we repeat the measurement. We have the broadband microphone. And in this case, I did not load an appropriate setup for this part type. I just hit it, and you see it's the spectra. The spectrum is totally other as for the switch cams before, but of course, it's a totally other part. Okay, this was an excursion to the lab, and from there we go to the shop floor. And how does this look like in, well, a real production environment? And what you see here is the installation for these belt pulleys, sound excitation via impact device, just as we have seen now, broadband microphone as a sensor. It runs fully automatic. Each part is tested. It's not so fast in this case, about 6 seconds cycle time. What is issued is pass-fail decision. It's the result. And it looks like this. So the part is hit in this case 3 times because of its rotational symmetry. This is in this case required to get all the resonance frequencies. It is placed by a gripper, and you see this item. It's not the microphone. It's just for marking the part. The parts are marked in case they are tested and assessed as a good part, so that the worker at the assembly line can see this is a tested part and it is an okay part. And well, what else can you see here? There's a part of similar shape, but with red paint on it. And this part is used as a reference part. You can test the whole signal chain by one single measurement. So the result from testing this part must be the same today, tomorrow, and in 1 month or in 1 year. And by testing it, you see that everything is all right, starting from the sensor, or let's say from the excitation technique, the sensor, the cables, the recording hardware. Well, that's it. And the other kind of application, we mentioned it in the lab, is a slide. And here in this case, sound excitation is done by dropping the parts on an anvil, on a hard metal plate. The sound recording is done with a broadband microphone again. And it's also fully automatic, tests 100% of production. It's significantly faster than the test station before, about 2 seconds per part. Again, the goal is a pass-fail decision. Here you had a time signal. Here you have a frequency spectrum. Here you see frequency spectra of many parts in false colors. Here's a result list with 2 faulty parts sorted out. And well, then there are some details about automation. This could be well applied to all cast or forged parts, as well as parts produced by powder metallurgy. So now I'm at the end of this part of the presentation, and I hand over again to Olaf.
Thank you, Michael. Yes, now we are more or less at the end of our short presentation. To summarize it a little bit, it's quite a important. We think that this is an important technology for current production lines. We can provide a comprehensive NVH solution and also a comprehensive NDT solution for your production lines. And all these bases on industrial experiences, on physical parameters, so that we can set it up in a way that it really fits to your production line. Michael, can you show the next slide, please? I did not. And now again, yes. So that's it. I hope we have a lot of questions that we can answer.